handful of engineers reportedly walked into work expecting another week of process optimization. Instead, the internet exploded with claims that TSMC's next-generation quantum node research had somehow leaked, and SMIC's engineers understood the physics within weeks. If that's true, it would be one of the biggest technology stories of the decade. If it isn't, the rumor itself still tells us something fascinating about where the semiconductor race has arrived. Because only a few years ago, nobody would have believed a headline connecting TSMC's most advanced research with China's largest chipmaker. Today, millions of people don't dismiss it outright. That shift in expectations is the real headline. The global chip industry has quietly entered a stage where the question isn't simply who has the best technology, it's becoming who can learn the fastest. And those are very different competitions. TSMC still manufactures the world's most advanced commercial chips. Apple, NVIDIA, AMD, Qualcomm, nearly every major AI company depends on its factories. Its process technology represents decades of accumulated knowledge, thousands of patents, and manufacturing techniques that cannot simply be downloaded from a server or copied from a document. Physics isn't a PDF. But manufacturing knowledge isn't magic either. That's where this story becomes much more interesting. The phrase, "cracked the physics," sounds dramatic. It suggests someone solved a scientific mystery overnight. Real semiconductor engineering almost never works that way. Modern transistor development isn't held back because engineers don't understand physics. Universities around the world teach quantum mechanics. Research papers are published every year. Scientific principles are surprisingly open. The difficult part is turning those principles into billions of perfectly functioning transistors on a silicon wafer, with defects measured in just a few parts per billion. That's an entirely different challenge. Imagine giving two chefs the exact same recipe. One owns the world's finest kitchen with decades of experience. The other has talented cooks but different equipment. Knowing the recipe doesn't guarantee the same meal. The semiconductor industry works much the same way. Every advanced node depends on thousands of manufacturing decisions that rarely appear in public papers. Material purity, process timing, temperature variation measured in fractions of a degree, chemical mixtures refined over decades, tiny adjustments that individually seem insignificant, but collectively determine whether a chip works or becomes expensive electronic waste. This is why export controls have focused so heavily on manufacturing equipment instead of textbooks. The United States didn't restrict quantum mechanics. It restricted lithography systems. That's a very important distinction. Still, dismissing Chinese engineers would be equally foolish. Over the past several years, companies like SMIC, Huawei, Naura Technology, AMEC, and dozens of lesser-known suppliers have expanded domestic semiconductor research despite increasingly difficult restrictions. Many Western analysts expected progress to slow dramatically after sanctions tightened. Instead, China redirected enormous resources towards solving the problems one step at a time. Not instantly, not perfectly, but consistently. There's also something else people often overlook. Engineering knowledge doesn't exist only inside laboratories. It moves through suppliers, through universities, through retired specialists, through academic collaborations, through thousands of researchers reading exactly the same scientific journals every month. One dry observation almost writes itself. Technology sanctions can delay manufacturing equipment, but convincing electrons to respect geopolitics has proven considerably harder. Here's the question that keeps bothering me. Suppose SMIC didn't literally crack TSMC's research in weeks. What if they simply became good enough that people found the rumor believable? That possibility may be even more significant than the rumor itself. Because once competitors become credible, every future breakthrough becomes harder to dismiss. And that's exactly where this story begins. There's a moment in almost every technology race when outsiders mistake momentum for a miracle. The Soviet Union had one during the space race. Japan had one in consumer electronics during the 1980s. South Korea experienced it with memory chips in the 1990s. China is living through that moment in semiconductors today. Every few months, another headline appears suggesting China has suddenly caught up. Then another group argues the reports are exaggerated. The truth usually sits somewhere in between, and that's where the interesting story lives. Take SMIC's 7-nanometer process. When researchers from Tech Insights examined Huawei's Mate 60 Pro in 2023, they discovered a domestically produced processor manufactured by SMIC using what appeared to be a sophisticated 7-nanometer class process. That surprised many observers because U.S. export controls were specifically designed to prevent China from reaching that level. Some people immediately concluded the sanctions had failed. Others insisted the chip was impossible. Neither explanation fully fit the evidence. The more likely answer was less dramatic. SMIC had found ways to squeeze extraordinary performance from equipment that wasn't originally intended for such advanced production. Instead of using the latest extreme ultraviolet lithography machines from ASML, which remain unavailable to China, they relied on older, deep ultraviolet systems and compensated with multiple patterning techniques. Think of it like drawing an incredibly detailed picture using an older printer. You can eventually reach impressive quality, but only after running the paper through the machine again and again with astonishing precision. It works, it's just slower, and much more expensive. That's why many engineers don't judge manufacturing success by asking, can you make one chip? They ask a harder question, can you make 10 million? Because semiconductor manufacturing isn't a science fair project. It's an industrial discipline. A prototype proves intelligence. Mass production proves mastery. This is where TSMC still enjoys an enormous advantage. Its factories consistently achieve yields that competitors spend years trying to reach. Yield simply means how many chips coming off a wafer actually work. Raising yield from 60% to 90% may sound like a small improvement. Economically, it's the difference between printing money and burning it. That's why customers trust TSMC with products worth billions of dollars. Reliability is often more valuable than novelty. But here's the subtle shift many discussions ignore. China isn't trying to beat TSMC overnight. It's trying to reduce the gap every single year. Those are completely different strategies. Beijing's semiconductor effort isn't centered around one company either. The National Integrated Circuit Industry Investment Fund, often called the Big Fund, has directed billions of dollars toward equipment manufacturers, materials suppliers, design software, packaging technologies, universities, and workforce development. Instead of betting everything on one breakthrough, the strategy resembles building an entire ecosystem capable of solving thousands of problems simultaneously. That's slower than chasing headlines. It's also how industrial power is usually built. Even critics of China's semiconductor program generally acknowledge one advantage: scale. Every year, Chinese universities graduate hundreds of thousands of engineers across electronics, materials science, physics, chemistry, and manufacturing disciplines. Not every graduate enters the chip industry, of course, but the talent pool is enormous compared with almost any other country. Engineering is partly about genius. It's also a numbers game. If enough skilled people attack enough difficult problems for enough years, progress tends to appear, even if outsiders underestimate it. This doesn't mean TSMC is standing still. Far from it. The company continues investing tens of billions of dollars annually into research, advanced packaging, transistor architecture, and next-generation manufacturing processes. Its partnerships with companies like Apple and NVIDIA create a feedback loop where cutting-edge chip designs and cutting-edge manufacturing evolve together. That's incredibly difficult to replicate. Still, one question refuses to disappear. If China keeps shortening the time between each technological leap, does the finish line matter as much as the rate of acceleration? Because history often remembers the leader. Markets, however, pay very close attention to whoever is closing the distance fastest. The temptation is to reduce this entire competition to a scoreboard. Who has the smallest process node? Who manufactures more wafers? Who filed more patents? Those numbers matter. But they don't answer the question investors, governments, and technology companies actually care about. The real question is much simpler. Who becomes harder to stop every year? That's where the story takes an unexpected turn. For years, analysts treated China's semiconductor industry as though it depended on catching one lucky break, a stolen design, a single breakthrough machine, or one extraordinary discovery. But that's not how technological independence usually happens. It happens when dependence quietly disappears. Consider semiconductor manufacturing equipment. A decade ago, Chinese fabs relied heavily on imported tools for deposition, etching, cleaning, metrology, and inspection. Today, companies like AMEC, Naura Technology, Piotech, and several domestic suppliers are steadily replacing portions of that supply chain. None of them individually matches every capability of the world's best equipment makers. Collectively, though, they reduce vulnerability. That's a very different objective. Think of a bridge. Most people notice the largest steel beam. Engineers worry about the thousands of smaller bolts holding everything together. Semiconductor manufacturing works exactly the same way. One missing machine can stop an entire production line. One domestic replacement removes a future bottleneck. Repeat that process hundreds of times over several years, and the industry begins looking completely different. This is why many sanctions have produced mixed results. They unquestionably slowed China's progress in certain areas. Access to cutting-edge EUV lithography remains a major obstacle, and leading-edge manufacturing is still extraordinarily difficult without it. That part is true. But slowing progress isn't the same as stopping it. Sometimes restrictions change incentives instead. Huawei illustrates this perfectly. After losing access to many American suppliers, the company couldn't simply wait for restrictions to disappear. It invested heavily in redesigning products, developing software, strengthening partnerships with domestic suppliers, and supporting local semiconductor capabilities. None of those decisions restored overnight access to advanced foreign technology. They did something else. They made Huawei less dependent on it. That's a subtle difference with enormous long-term consequences. Here's where I think many debates become too simplistic. One side claims China is already equal to TSMC. The other insists China remains hopelessly behind. Both arguments overlook how technology races actually unfold. Leadership isn't binary. A company can remain the global leader while competitors become dramatically stronger. Intel once dominated semiconductor manufacturing so thoroughly that its position appeared almost permanent. Yet within little more than a decade, TSMC transformed from a contract manufacturer into the world's undisputed production leader for advanced logic chips. Few people predicted that speed of change. Industrial history rarely moves in straight lines. It tends to move gradually, then suddenly. I'm not completely convinced anyone can accurately predict where the next major inflection point will come from. Maybe it's advanced packaging. Maybe it's gate-all-around transistors. Maybe quantum computing changes the industry's priorities altogether. Or maybe artificial intelligence itself begins optimizing chip manufacturing faster than human engineers ever could. That last possibility deserves more attention than it's getting. AI is increasingly being used to optimize circuit layouts, improve defect detection, refine production scheduling, and accelerate materials research. Every percentage point gained through machine learning saves millions of dollars across high-volume manufacturing. Imagine both sides using increasingly powerful AI systems to build even better chips that run even stronger AI. That's not a race, that's a feedback loop. Which brings us back to the rumor that opened this story. Did SMIC's engineers literally solve TSMC's next-generation research within weeks? Based on the public evidence available today, there's no credible proof that happened. But in a way, that's no longer the most important question. The more important one is this. If every year the technological gap becomes a little smaller, at what point does the conversation stop being about catching up and start becoming about competing? The semiconductor industry has a habit of humiliating anyone who makes absolute predictions. People once said Japan would permanently dominate memory chips. Then South Korea rewrote the market. People later argued Intel's manufacturing lead was untouchable. Then TSMC quietly became the company every major AI firm now depends on. History doesn't repeat perfectly, but it does punish certainty. That's why I think the discussion around TSMC and SMIC needs far more nuance than it usually gets online. TSMC remains the world's benchmark for advanced semiconductor manufacturing. Its ecosystem, customer relationships, process maturity, packaging technology, and production yields are still incredibly difficult to match. Companies like Apple, NVIDIA, AMD, and Broadcom aren't choosing TSMC out of charity. They're choosing it because billions of dollars depend on chips arriving on time, performing exactly as designed, and maintaining extremely low defect rates. That trust took decades to earn, and it can't be copied in weeks. At the same time, dismissing China's progress has become an increasingly risky habit. Every major round of restrictions has forced Chinese companies to answer the same uncomfortable question: what can we build ourselves? Sometimes the answer has been disappointing. Sometimes it has surprised almost everyone. What's remarkable isn't that every domestic replacement is world-class today. It's that there are now domestic replacements at all. 5 years ago, many experts believed several parts of China's semiconductor supply chain would remain permanently dependent on foreign technology. Today, the conversation has shifted toward how quickly those remaining gaps can be narrowed. That's a very different debate. Here's my opinion. I don't believe the future semiconductor race will produce a single winner. Instead, I think we're watching the birth of two increasingly independent technology ecosystems. One centered around companies like TSMC, ASML, NVIDIA, Synopsys, Applied Materials, and other Western and allied suppliers. The other gradually taking shape around SMIC, Huawei, Naura, AMEC, Empyrean Technology, and a growing network of domestic Chinese equipment, software, materials, and design companies. Neither ecosystem will be completely self-sufficient for quite some time, but both are clearly trying to become less dependent on the other. That's probably the biggest strategic shift of this decade. For ordinary people, this isn't just an engineering story. Every smartphone upgrade, AI service, cloud platform, electric vehicle, medical scanner, and even modern household appliance depends on semiconductors. If the global chip industry fragments into competing ecosystems, consumers may eventually notice it through higher costs, different product availability, and slower international technology cooperation. The consequences won't stay inside clean rooms. They'll reach our wallets. There's also one final question that's worth asking. What if the biggest advantage in semiconductor manufacturing isn't today's technology, but tomorrow's learning speed? Because that's what this competition increasingly resembles. Every fabrication run generates mountains of production data. Every design teaches engineers something new. Every manufacturing problem solved becomes institutional knowledge that compounds year after year. Knowledge behaves a lot like compound interest. The earlier you invest, the harder it becomes for others to catch up. But compound interest also works in reverse. A fast learner can reduce surprisingly large gaps over long periods without ever making a single dramatic leap. That's why headlines claiming someone cracked the physics in weeks are probably missing the real story. Physics wasn't cracked. Manufacturing wasn't magically copied. If anything, the semiconductor race is becoming more demanding, not less. Winning will depend less on one spectacular breakthrough and more on who can solve 10,000 microscopic problems faster than everyone else. My prediction is this. Over the next decade, the conversation will gradually shift away from asking whether China can match TSMC at the most advanced node. Instead, the focus will be on whether the global industry can continue operating as one interconnected system, or whether two parallel semiconductor worlds become the new normal. And if that happens, today's rumors will be remembered as background noise. The real story was never about one leaked node. It was about a global industry reorganizing itself in real time. We'll find out soon enough which strategy proves more durable. If you enjoyed this analysis, subscribe and stick around. The next chapter of the chip race is already being written, and it's likely to be even more surprising than the last.